Saxon Algebra 1, Lesson 61. The topic for the day is subsets. Subsets are fun and easy, and we are going to use this in the future. Right now, you're going to be like, this is a really random lesson, and what does it have to do with anything? Don't worry, we're going to put it to use. All right, we talked about sets, and we learned that when you write numbers inside the little whoop-de-doos and you give them a letter name, that's called a set. We learned that this set has elements. We could say that 2 is an element of A, and we could say that 5 is not an element of A, right? We talked about that. These are members or elements. And sometimes we looked at 2 sets together. And now what we're going to do is talk not just about the members, but about whether one set fits into another set. And we see here that all of the members of B are also members of A. So we can say that B is a subset of A. Is a subset of. That's what this like sideways U thing means. Okay, so B is a subset of A because every member of B is also in A, but A is not a subset of B. Is not a subset of, right? With the slash out. You get it. It's cool. Okay, let's do a problem and see if we've mastered the concept. Example 61.1. Okay. What John is going to do, here, let me cross out the part I don't need you to look at. This is how the problem looks. Given these sets, D equals 0, 1, and 2, F equals 1, 2, 3, and so on. Aha, that's an infinite set, right? We learned that. This is a finite set. This is infinite. And G equals 1, 3, and 5. Tell which of the following assertions are true and which are false and why. Okay, that sounds like a lot. And look, the questions are really easy. I'm going to move the book and I'm going to copy these down. You would not need to copy them down. You can just look in your book when you do the problems. But I want you to be able to see both at once. D is 0, 1, and 2. E is 1, 2, 3, and so on. And G, it skips from E to G. I mean, go figure. Maybe that's what the G stands for. G is 1, 3, and 5. Okay, so here are the 3 questions. Or they're assertions, right? E, sideways U, G. Remember, this means E is a subset of G. So let's see, is every element of E represented in here? I don't think so. This is false. And why, do you ask? Well, I mean, the easiest way to say it is that all elements of E are not in G, which seems silly to even say, right? That's the whole definition. All elements of E are not, we'll use a fancy word, members of G. There, John should like that, right? I didn't use a capital at the beginning, sorry. Okay, the next one is G G, remember this means is a subset of. G is a subset of E. Okay, G is 1, 3, and 5. This includes that, right? Because it keeps going. So we say true. And we would say all elements of G are in E. Okay. And then the last one is D is a subset of E. D is a subset of E. Aha! I see that 0 is in D, but 0 is not in E. So this one is also false, isn't it? E has no 0. Ah, how could it? Okay, so these are true. These are called assertions. We don't know for sure if they're true or false, and that's what our job is to test those, okay? So we got all of these right. Yay, happy days for us. All right, now let's apply this. Now what I want you to do now is wherever you are in your notebook, flip so you have a fresh piece of paper. I know you're writing down everything that I tell you because I tell you always to do that. But make sure you have a fresh piece in front of you now, just like I do. And we're going to make a chart that's going to take up most of this page. You can draw it as pretty much a square. And I want you to make it big, please. Pretty please. Okay. And I want you to draw a line there to divide that part off. And up at the top, we're going to give this a name. Real numbers. Okay, I'm going to come back to that at the end and address that title. Now, what we're drawing is a diagram that shows how all the different subsets of numbers fit together. All right, and we're going to start at the very middle, the easiest part where you began when you learned to count. You were a tiny little baby and you were fresh out of the bathtub and you were wrapped up in a towel and you were sitting on either your mother or your father's lap. Probably both of those things happened. And they were drying you and snuggling you and they started counting your little pink fingers and your little pink toes. And the way that they counted them was to say 1, 2, 3, 4, 5. And then maybe they switched over to your other foot and kept counting 6, 7, 8, 9, 10. And maybe they grabbed one of your brothers or sisters and started counting theirs and went on and on. This goes on infinitely. But this is how we all learn to count. And that is why these are called the natural or the counting numbers. Okay? So that is the first subset of numbers that we want to talk about. Later, you got a bit older and you stuck your hand in the cookie jar one day and felt around and realized there were no cookies in there. And you learned a new number, and that is 0. The meaning of 0 became painfully clear to you and your stomach, and you expanded on your concept of numbers. And these we call the whole numbers. You got older, and you started to have a little bit of pocket money. Maybe your parents paid you an allowance. Maybe it was birthday money. I don't know. But at some point, you wanted to buy something that you didn't have money for, and you convinced someone, your mom, your dad, one of your brothers or sisters, to loan you a little bit of money. And you began to understand the concept of negative numbers. Because now you didn't just have 0 money, you owed someone money. Let's say you borrowed $2, right? You learned that -2 is a value. You didn't just have 0 money, you had less than 0, didn't you? So you began to learn about negative numbers. Now notice that there's no fractions or decimals involved in this. We're just dealing with the regular, the friendly numbers, as I often think of them. Okay, and we call those numbers the integers. All right. Notice that each time we expand our understanding of numbers, the subset grows and gets bigger. All right. That's the way it works in real life, and that's the way subsets work. Now, you got older and you learned about splitting pizzas with your siblings. Actually, those of us who have siblings, we learn about rational numbers right away because rational numbers include any number that can be written as a fraction. So that includes things like, for me, the magic fraction was 1/4, because that was, I have 3 siblings, so everything was divided in 1/4. But it can be weird decimal numbers, or it can be percents, right? They can be negative as well. I'll just pick a random one. So you began to learn about fractions, decimals, and percents, and we call those rational numbers because it's any number that can be expressed as a fraction. And fraction and rational are 2 words that are related. You can see they're not spelled exactly the same, but they have a similar look to them, a similar root, okay? So these numbers, all natural numbers, whole numbers, and integers, are all subsets of the set of rational numbers, and rational numbers in turn are a subset of the real numbers. Now, there's another group of numbers that are real. There's a subset of the reals, but they don't connect with these guys at all, and they are called irrational numbers. And they are fun because they are quirky misfits. They are like in Rudolph the Red-Nosed Reindeer, the land of the misfit toys. That's what they are. They are numbers with non-repeating infinite decimals. And the star member of the club is pi, our number that relates the diameter of circles to their circumference, and it relates the radius of circles to their area. Pi, we all know, is 3.14 la-di-da-di-da-di-da-di-da-di-da-di-da, right? It goes on forever. Pi is a great example. The other great example is the square root of 2. It goes on infinitely with a non-repeating decimal pattern. These are irrational numbers. They are a subset of the reals, but otherwise they don't have anything to do with these guys. Okay? So these guys, these 2 sides, are not subsets of each other in any way. They're only related as real numbers. Now, every once in a while, I get a little smarty pants student. It could be you because we're not together, so you could be thinking this. And that's okay. Who say, the real numbers, some numbers are unreal? And I'm going to give you spoilers to Algebra 2. Yes, there is another group of numbers that are not a subset of the reals. They are called, ready? Make sure you write this in. They are called imaginary numbers. Oh, yes, they are. You will learn about them next year. They're really cool and fun. Imaginary numbers don't interface. They don't connect. They're not subsets with the real numbers at all. But together, the imaginary numbers and the real numbers make up a new set of numbers called complex numbers. Okay, we're not concerning ourselves with those just yet. We're keeping it focused in on the real numbers. But what we're really going to focus on is this progression here from natural or counting numbers to whole to integers to rationals. And that is what our problems are about. So let's keep this in front of us. Example 61.2. When you sit down to do your homework for lesson 61, the first thing I want you to do is copy this into your cover of your book. It's really important that you be able to reproduce this. It's okay if you have to look at it right now, but eventually I want you to have it memorized. Eventually. Okay, 1/2 is an element of which subsets of the real numbers? Okay, is it a natural or counting number? Well, no, because hopefully you don't have a half toe. I mean, you could, but it's not a natural number. It's not a whole number. It's not even integer, because integers don't have any fractions. It's all the way up here. It is an element of the rational set. So that's our answer right there. Okay, 61.3. 5 is an element of what numbers? Okay, well, 5 comes all the way down here to the natural numbers, right? And so we know these numbers here, it's kind of like those stacking cups you probably had when you were a little kid, where once it fits inside of this one, it fits inside of all the others, right? So it is a natural, a whole, an integer, and a rational. So we have to write all that down. Natural. You can write natural or counting. Whole, integer, and rational. And John throws in, he throws in the whole category too. He calls it a real number. Okay, cool. We can throw that in, right? So boom, 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 boom. They all fit inside of each other like those little plastic cups that stack together so nicely. I always like those cups. 61.4. 3 square root of 2 is an element. Aha! Square root of 2, that is a trigger. Look, there it is right there. So multiplying that square root of 2 by 3 doesn't change anything. It still is going to have infinite non-repeating decimals. And so we know this is an irrational. And by the way, these are all right. I would not steer you wrong. And 5, all right, I'm going to skip. I'm out of room here, but I don't want to turn the page away from this, so I'm going to use my little auxiliary book that I always have here with me. Ready? Okay, so we're supposed, these are more true and falses. Okay, so this is example 61.5, and we're supposed to tell where the, excuse me, tell whether the following statements are true or false and explain why. A, the set of reals is a subset of the set of integers. Okay, the way this reads is that this is the smaller one and it fits into that one. That's not true. It's the other way, right? Reals are bigger than integers, so this is not true. It's the other way around. B, the set of irrationals is an element of the reals. Irrationals and reals. Yes, that works, doesn't it? These are part of that. Okay, true. C, the integers, oh wait, no. Irrationals are a set of the rationals. That sounded wrong how I said it, right? The irrationals are a subset of the rationals. I mean, we can just tell from the words. These are the irrationals. Those are the rationals. Ne'er do they meet. They don't fit inside of each other. So no, it's not a subset of that. What are you, crazy? Here, I need to bring this up so you can see better. Are you mad? No, the irrationals are not part of the rationals. That's the whole point. You can't express these as fractions because they repeat forever and no, they go on forever and they don't repeat. Which brings up an interesting point. Does that mean that repeating decimals that go on forever are rational? Yes. So I'm just going to make a note of that. Includes infinite repeaters if they have a pattern. And it's if they have a pattern. They have to have a pattern to their decimals, to their repetition. And then we can write them as a fraction. And at the end of Algebra 2, we are going to learn how to do that. And I'm telling you, it's a trick you'll be using at parties. I promise you. Okay, so irrationals don't repeat. Rationals do. They're not connected. And D is wholes are a subset of the naturals. Okay, let's take a look at that. Wholes and naturals. Wholes are a subset of the naturals. No, it's the other way around. Naturals are a subset of the wholes. So that is false. John, are you serious with this? And here's our last one. Integers are a subset of the reals. Integers are a subset of the reals. Yeah, that sounds good. Integers fit into the reals. So that one is true. I did not write down the reasons this time, but we talked about them. And they're kind of obvious, you guys, right? Either all the members are an element or they're not. Okay, so this is the kind of problem that we're doing in lesson 61. Like I said, we're going to use this information later to help us sort out some problems. It is a really great organizer that helps you see how all of these different ideas fit together. It's not just randomly theoretical. It has a practical use. We're just not doing that in lesson 61. Okay? Okay, goodbye.